Welcome. I'm Jansen Bennett, Preservation Architect with the Utah State Historic Preservation Office. I'm glad you're joining me as we travel through the history of the Olmstead Power Plant and discuss the architectural significance of its buildings. Our journey begins in the early 1900s, when hydroelectric power got its start in Utah at the mouth of Provo Canyon.
The Olmstead Power Plant is really similar to lots of power plants that you'll see throughout Utah in its architecture. So it was built of ashlar masonry, which is a fired clay masonry. And the reason for that is that it was fire resistant. So if you think back 100 plus years, fires were one of the big concerns in any type of factory or power plant or really any building, because we didn't have the same type of firefighting technology that we have now. And so it was really difficult to put out fires. Also, you can see the really big windows, which is kind of counterintuitive to the way we think of a factory today. Factories today are typically, big metal boxes. But historically, they didn't want to use electricity and sometimes didn't have electricity to actually run and see the machines. And so the larger the windows, the better, so that it would have a safer, more well-lit internal environment.
So this is a run-of-the-river power plant. It's not at the base of a dam like Jordanelle has a power plant. We divert the water about 4.5 miles up the canyon at the Olmstead diversion that comes along the hillside. You can't see it. It used to be the old green pipe. We have a stick of it or a segment of it out there.
And if you follow the water down from up at Trial Lake at around 10,000 feet, the water storage up there happens all winter long. And then we rely on that April through July runoff to capture about 80% of our water supply for the Wasatch Front. Power is stored at Jordanelle. It's conveyed down through the Provo River with an agreement with Deer Creek, and there's some foreign sources that come off the Duchesne and the Weber. But that water travels all through Jordanelle and is generated at the 13 megawatt plant up there. It's released based on run of the river and the water calls for their water customers. In cooperations with Deer Creek and Provo River water users, it gets kind of conveyed through Deer Creek and it's generated there again. And then once that's released into the Provo River again, it's diverted at the Olmstead intake. It's about 4.5 miles upstream here. And then based on where the water is either going to the municipal and industrial system out to Jordan Valley, through treatment plants all through Salt Lake County, West Salt Lake Valley, all that area has a piece of that. Jordan Valley Water Conservancy District, Metropolitan, Salt Lake Sandy, all those guys have water rights and use CUP water. But without this plant, we can't, there's a lot of old power rights, as like Chris said, and it's very complicated on how we store and interfere with ourselves and replace it through other diversions off the Colorado through a lot of different ways. But that's why we had to build the new plan, is to maintain those junior water rights.
Can you talk a little bit more about the development of everything? Because with such a large complex, I'm assuming it wasn't all built at the same time.
No, it wasn't. So in early 1990s, 98, late so they actually had a power plant that was up at the Nuns Park. And so they were generating a little bit of power there. And then they actually wanted to dam up the Provo Canyon. The same time they were doing that, there was a major failure back in Johnstown, Pennsylvania, where there was a major dam failure. The citizens downstream of us said, "No way are you building a dam." Well, we'll get there right now, but back then they said no way. And so he figured out he could bring the water down the canyon, generate more pressure, more head, and generate more power to send out to his mines.
This is the pressure box up at the top of the hill. And this was the unit 4 that came in. We'll show that very last. These are the 3 units we were looking at earlier coming down. But this was a way that they controlled the water that was going through this rock tunnel. So I talked about the water being diverted and then going into tunnels. This is what it was, a hand bored. They'd go in with chisels and then they would use dynamite, and the next crew would set up and come in. The miners did this by hand. It didn't have this really nice concrete floor until the 2000s. It was a wood floor. This is where my coworkers and I started out removing this by hand and hauling it out of here.
How long did that take?
a whole winter.
Yeah.
But we only did the sides one winter, and then they had to go back in and take out the bottom. And when they did that, there was great big, the floor looked like the roof. How's that? And so the water profile wasn't the best. So then we came back in the 2000s and poured the concrete floor in it. And we had lighting in it because it was an open channel tunnel. The rails that are put in were because of the construction. That's how they put the new pipe back through there.
Okay.
So picture the water coming this way, flowing, but it was only 3/4 of the way up, and it was open channel until it got to here. And then if there was any kind of a load rejection, the big wooden gates down here would close. And that's what you guys would see up Provo Canyon flowing over the wall. Was when they had a load rejection here at the plant, the water had to go somewhere. I tease people, this is why there's hardly any trees left in Provo Canyon, because they all used it for this, but it's not true. But they did use a lot of timber, and so it was just a wood box that went 4 miles up the canyon, all the way down, and it broke a lot, if you can imagine that.
This is the new power plant that was built just east of the historic power plant and was actually built to replace the historic power plant. And I just want to do a quick compare and contrast of the architectural features. So you'll remember that the historic one was built entirely of ashlar masonry. In a nod to the historic power plant, this one has ashlar masonry, but it's built within a concrete frame. And this is a fairly typical construction method for utilitarian buildings, where they don't necessarily need to look pretty, but they do need to function really well. And those will carry a lot more weight than the ashlar masonry piers, as well as be more resistant in a seismic earthquake. You can also see that they kept the windows and used windows that have a similar styling, but you can notice that they're all using opaque or frosted glass. The light isn't the same concern. These are there mostly for aesthetic reasons as opposed to the functional reasons that the historic windows served.
Some of the things I like to point out, Chris, is how the key notches in the concrete were all formed. This is prior to AutoCAD. And it's amazing the thoughtfulness that went into the designs on some of this stuff without having those types of tools that we have today in our current engineering practices. Amaze me to this day. So when you run a hydro unit, what you have on them is like these Venetia lines that control the flow, and they're called wicket gates. And even today, you can actually manually engage with one hand. I can still control the armatures of just how well things are balanced and how smooth all the machine work was done on these units, 100 years later.
One of the really nice things about utilitarian architecture is every part and element of the design serves a purpose. Unlike lots of the kind of more traditional things that we think of as architecture, which have a lot of kind of styling added to them, everything here serves a purpose, and you can really see that in the floor plan. So this was the historic loading bay. So a place to bring in and out equipment and other things that were necessary for the function of the plant. And then over here, you have this kind of mezzanine level, which is where all of the generators were serviced. And so you had to have this second level to really be able to get to all of the machinery that was necessary. And it's adjacent to the loading dock so that you could bring in all of the tools required without having to go up or down stairs. And then over here, you have this open space, not because it would be a really great place to kind of look down and see the grandeur of space, but just because it wasn't necessary. It also allowed light to enter the lower floor where other work would be accomplished. Essentially, the whole campus was largely self-sufficient. That, they had their own laboratories, their own blacksmith shops,
Yes.
and workshops and everything. Did they build all the turbines?
No.
Or were those brought in?
They were brought across country by railroad. And if you come over here and zoom in on here, you can see their General Electric right out of New York. And so those are the original nameplates. So this is the generator and the bearings, and the actual turbines are in these units behind me, and that would create the force, and then the draft tube would go down into the telerace through the campus, which is a really nice block wall. So the pressure would be coming up, and then it's going out this way to the telerace. And so it's kind of coming underneath the ground, and then as it released, it's going this way, and then down underneath to the telerace. So when all the units are combined, the full water right for this plant was 429 CFS. So for the non-water guys out there, 1 CFS is roughly 450 gallons a minute. And then more water geeky math. If you were to flow that 1 CFS for one full 24-hour period, you get about 2 acre-feet. Acre-foot of water is about a football field with a foot of water on it. So when we talk in our world, we're talking in cubic feet per second. So the whole entire plant with everything running was a 429 CFS plant. And then really noisy in here though, guys. This stuff was really clunky and noisy. And if you can't see it back here, they were using the slip and ring technology on the excitation, where today most of that stuff is brushless. And so you could get some arcing and stuff going on. And even the building would leak and create arcs of electricity. And there's one story of back in the shop area of an early young man that was his first day on the job. And he got hired, and they were all at dinner. And this young man was had all these alarms go off that he talks about in his journal. And everyone jumped up, and dining with the nuns was a formal event. You actually dressed up. If you got invited, you're in nice dress clothes. And the plant had an issue, and he come running in. And back then they were wood polished floors. That helped with the insulation. And so he come flying in, and he hit that wood polished floor, and he slid. And he was sliding underneath an arc flash, a big plasma arc. Now picture a young man in the 1904s, doesn't know what electricity is. What would be going through his mind that you've got lightning inside a building, and this is like your first day on the job, first couple days, you're like, what have I got myself into? Technically what would happen is as it's a governor, and the centrifugal force in those balls would go out, and it helps regulate the speed of the unit. And they just sit and control it. But have you ever watched Willy Wonka in the Chocolate Factory in the elevator? He's got one of these spinning around. I don't know why. And
It looks cool.
and the way you control the speed of a generator is you open up more water to it, and then it produces more energy, and you can kind of control the speed. And the speed is really sensitive because the number of the poles that go around the generator determine that 60 hertz at the time. And so in order to have really constant power, you got to have the right voltage, the right frequency, and everything else. And these governors just help control that. And they were made by Alice Chalmers, the actual tractor manufacturer.
Or you have a certain RPM that you find you call it the sweet spot.
Yeah.
Optimal fuel economy. So what Paul is describing is you get this turbine to be spinning and find its sweet spot that's consistent, and you keep the flow coming in, the head or the pressure of the water, that it's coming down at a certain rate, that it stays as consistent as possible, so the generator with the power going out goes, and you don't have big hiccups or issues downstream.
And then this was just the manual control, guys. You can try it. Someone else needs to be in the camera. So when you're doing that, you're actually controlling the wicket gates, which would allow the more water to go out or through the turbine. And so you can see how smooth that is. And then their neutral was just essentially slide it back. And so when they needed to take control, they just pushed that in and then they could adjust stuff. If you walk over here, this is actually a lighting panel with just open bus. And I mean, so what I do is a lot of times I'll have the kids come in and they're like, hey, will you turn the light on? I tease them. I'm like, no, like act like I'm getting shocked. And they're like, oh my gosh. But can you imagine having wet hands and stuff? So, you know, you just had the armatures here, you had your voltage on here and your fuse block. And so you just had an open bus like that. And so it was really cool. If you come with me here, there is another little turbine right here. And there's a terminology out there in the power world of what's called a cold start plant. And this plant had the ability to generate power kind of on an island by itself, where a lot of the power plants today have to have the grid there to synchronize to. We're all synchronizing to the same heartbeat, that same 60 hertz. But this plant was unique that it didn't have that back in 1904. It had to create that heartbeat for itself. And so this was a Pelton wheel, where these were Francis turbines. And this Pelton wheel system, they would start this up. And you can see the brush system here. So this was actually a DC generator that was used to create the DC current that needed in the coils to make the magnetism. And so they would be running this to run their units, and they could absolutely be an island without the Western grid and produce the power to go out to Mercer, because the grid didn't exist back then. So this was what was called a cold start plant. You can see the Francis turbine inside, so I don't know if you can...
I can zoom it.
You can zoom over here?
I can also jump in it.
So if you kind of rotate your camera to those who are watching it, I wanted to point out, this is what happens over time. You get holes and cavitation and wear and tear on these turbines. You can kind of see the holes in the rust, and that's one of the reasons why we build a new plant, is because when we start evaluating the condition of this plant, and we need to continue to be able to maintain those generation commitments, it was cheaper for us to build new ones.
In the center of the floor plan, you have this operations center, which, if all of the generators are kind of the working like arms and limbs of the factory, this is the heart and the brain. And now all of these windows have been covered with kind of information as part of the museum, but historically they will have been clear and will have provided a really open, clear sightline, so that the people working in the heart and the kind of mind of the plant could see everything going around and would be able to kind of problem solve and kind of nip any problems in the bud before they became emergencies.
It came out of a really early generation control system. And we call this the Christmas tree because this was their dials. And if you look real close, I think it even says where this one came from, West Logan. It was left here in one of the garages, and we were able to put some new glass in the broken dials in and keep it and preserve it. And one of my favorite things, you guys will love this, because everyone loves their iPhone 15 or whatever we're at now. I mean, there you go. And it was a party line for I don't know if anybody even understands what that was.
It's worth explaining.
So the way the phones used to work around the homes was they had their rings. So my mom's house would have been like ring 3, so a ring, ring, ring. They'd know that was their house. But everybody else could listen in on the conversations because it was one phone line. So yeah, how would you like that today? That with our iPhones. So anyways, control systems were in use. This was an 80s upgrade. It did have some modernization. It went on from the 80s clear into 2015. They had some automatic controls, but you guys watching this can kind of see what it took to run the plant. The Nunn brothers were coming out of Colorado, and they were miners, and that was the interest in their hearts, was to come and bring mining. And then their stories of how they dumped a big bag of gold dust on a desk to Westinghouse and asked them to help them develop AC. And that's where the beginning of Olmstead starts.
One of the architects' last name was Olmstead, and he happened to pass early on. He was a really good friend with the Nunns, and so they named the place after him.
Oftentimes, you'll drive past a power plant, whether it's in a canyon or in the middle of a city, and you'll see all of this kind of really ugly stuff stuck to the side of a really pretty historic building. And you'll think, why in the world did they design it like that? But the fact is that all of these historic power plants were built really early, so the late 19th to early 20th century. And technology has changed a bunch since then. And so as part of the story of these buildings, all of them have this additional equipment that either for safety or functional reasons isn't located within the power plant itself. So all of this was added probably a little bit at a time throughout the 20th century. So you can see it, and it's not that it was poorly designed, just that technology changed over time.
This is the foundation and the walls being formed. And then look at Orem. I mean, this is amazing. So the Central Utah Water offices is right here, and none of the 800 north interchange into the highway going up the canyon. But this bridge is still here. Those that like to travel on the trail will go over that old metal bridge still. But this was the train tracks for the Heber Creeper that would take you back and forth up a Provo Canyon. And this is the Provo River right here. And you can still see some of the irrigation systems and stuff early on that were transporting water, but there is no homes in there. It's just way open. So to have facilities in here with running water and sewer systems and everything else early on in this era was pretty rare.
So the building behind me is the Telluride Institute. And when this power plant was first built, it was one of the first in Utah. Because electricity, and especially hydroelectricity and alternating current, were such new technologies when the power plant was first constructed, it also required a large workforce that didn't exist already. There weren't schools or places to go to learn how to work at a hydroelectric plant. And so Mr. Nunn established the Telluride Institute, where he would hire people on. He called them pinheads because he would move them around on a board. But essentially, the role of every pinhead was to come and be a student, where they would learn, go to classes in this building, and then have hands-on experience working in the hydroelectric plant. And the Telluride Institute, fun fact, is still going on. Not in the building behind me, but now it's in Cornell in New York.
So the miners were living in tents in the winter. His ones that were achieving and growing up and learning would end up in warm buildings. You can kind of start to see little camps around. And so we're right here in the powerhouse, right here. Mm-hmm. And then this was one of the admin buildings of the power company before they went away. But this building still exists right now. This is a 4-story, we call it the training center. It's also referred to as the quarters building. And when we talked about the carpenter shop, it was here. I'm kind of forgetting now over the years. This is the blacksmith. These are the warehouses here. And then if you look across in here, you can see the lab, and then right here there was a house that the superintendent lived in at one point. And then right over here, there's a cottage. And so there's a bunch of different houses. So
over time, lots of the buildings and structures that were here have been demolished. The ones that remain are really interesting to look at their styling. So this residential building to the south, the workshop building to the east, and the Telluride Institute all share really similar architectural elements. They're all made of masonry. They're all made of light-colored masonry. And you can see some distinctive elements that are carried throughout all of them, from the kind of interesting railing details on the residence, as well as the way that the upper portions of the windows are divided, as well as the coining on the corners of the masonry buildings. All of these elements help to know that these were all buildings owned by the company. So this residence was for the caretaker or owner. The Telluride Institute is where people were trained and taught how to work at the plant. And the workshop is where lots of the kind of smaller elements were worked on, all to further the work being done here. The additional residences that we can see were built, but don't serve the same purpose in directly tying into the factory and the company. And so they have separate detailing. You can see kind of the stacked, more natural stone masonry, as well as the kind of more plain, less detailed elements on both of those buildings.
There was a big debate going on early in the early 1900s, 1890s into the 1910s, where the country was going to be AC or DC. And it's been said that this location was generating some of the very first long distance AC generation in the country, in the world, at 44,000 volts. Driving in, you came across a house that had a flat top roof on it, and the name of that house was the House of Ideas. What that was a house that they built to demonstrate to the rest of the world what electricity can do for you. It was an all-electric house. People from all over the world, from different countries, came here to look at the house, to look at some of the first clothing washing machines here, and an electric stove, and an electric heater, and another version of really early AC electric stove. And so the idea behind it was to come and talk people into moving into that direction of having an electric house. And so that was something that was built here. And so this is what this whole corner is representing, is capturing that history there of that. And so when we talk to the nuns and their ancestors, they're more interested about that house being maintained, which is pretty old, then this is what they're really interested in. So this is the shop, and the shop was designed to bring the units in from the railroad. And if you can see right here, as we were constructing the place, we actually found some of the old rails that were buried, and this is how they would bring the units in from New York. And so we're talking 1904. You can see some of the old lathe work, some of the original motors. This was came out of what they called the blacksmith building, where they would founder and produce all their own tooling. You can actually see that building on a program, Granite Flats, BYU, and the old Jeeps pull up to a little old white shack, and that was the blacksmith shop. So as you're coming into the plant, picture this as kind of an unloading dock, and a lot of this was done by hand. You can actually see the crane works. There was no on it, was all done by hand this day, because we actually used it to move some of the stuff around. And they would bring in the units from New York, where they were being made, and Niagara Falls and that area was where a lot of it was being developed by Tesla himself. And during the time they were building this plant, the railroad went on strike, and so some of the workers went and stole the rail car and got it here on their own and pulled it in to continue their project. So these are stories we've read through books and historians and stuff that have collected this data over time. When we started evaluating the condition of this plant, and we need to continue to be able to maintain those generation commitments. It was cheaper for us to build a new one. In the 80s, this plant went through a major upgrade right before CUP and stuff, and so they did a lot of money on it. So it had already gone through several decades of usage and wear and tear, rebuilds, wear and tear. You come up to 2015, we spent a good portion of a year or more evaluating it to figure out if it's cheaper for us to build a new one or do another renovation. And that's when the decision was made that we were going to build a new plant. And then that's when all the preservation and all the other stuff came in too. But we're not going to get rid of this one. The water you're hearing, this is kind of Chris's design. Get over here. This is actually a false floor because the water's coming in from the groundwater and collecting around the base, and then it's getting collected and getting pumped back to the river. But this is kind of a hollow floor.
You raise the floor up, like post to travel and collection action.
So
It's always kind of come in here.
but there was so much concern in preserving the architecture, even the insulators, just lots of these things. So it caused complications on how to do that and not affect the actual feel of the building. And they took a lot of time working on that. So, and then of course the coating on the floor wasn't original. That just helps us keep it clean. As I'm out on Facebook, it's really interesting. People in Orem are posting pictures when they worked here. I think Chris has seen a bunch of those. Where'd you go, Chris? And there's so much interest in this place from the public and families that grew up here.
I imagine this was a fairly long process between so you mentioned that the plant was in operation until 2015, and so then previous to 2015 you started building this new power plant, and then I can just imagine it was a lengthy process to finally get to this point.
Right. We started talking about, I started getting involved, I think, in 2012.
Okay.
The planning for the new power plant started about then. And we did all the clearances, coordinated with the SHPO, with you guys, because we knew we were going to have to take down some buildings. We wanted to preserve this. But we didn't start construction on that until 2015.
Okay.
And then probably 2016. It was finished in 2018.
Okay.
And we started this, actually, the design in like 2019, and then construction in 2020. So yeah, it's a long process, absolutely.
Yeah.
We, the Central Utah Water and the federal government, became the owner. We were always the owner. Well, we were the owners since about 1990. We let Pacific Court stay here and regenerate some of the capital investment that they got. And then they left in September of 2015. We built another power plant across the parking lot here just to the west, which generates 13 megawatt plant, Paul?
10, sorry to correct you.
Okay.
A little over 10 and change.
And that is largely water that we can store in Jordanelle Reservoir through a complicated water rights process. But we had to build another power plant to protect water that's in Jordanelle, which provides water to about 1.6 million people in the state of Utah.
When you look even at the new stuff, you still see a lot of the 100+ year designs because this stuff was so it hasn't changed that much. When you look at the Francis turbines, they're all handmade. They all have their little characteristics on efficiencies, and it hasn't changed over the years. It's gotten better, the materials have gotten better, the engineering's gotten better, but the principles are still the same. They really are.
Thanks for joining us on the tour for Central Utah Water Conservancy District. Our water is our business. However, there is a component of power with that in hydroelectric power generation. This is our second hydroelectric power plant behind this one, the new one. Where we were over here, the hydroelectric power plant is actually owned by the United States. Everything from there this way is owned by Central Utah Water Conservancy District, and we bought it to help protect our investment over there. and we spent a lot of money and time and energy and effort here. We plan on maintaining and updating as we need to this area for the foreseeable future.